Okay, everyone, so we're back for part three of module two, where we're going to introduce hydrostatic forces on plane surfaces. So again, we're still looking at static pressure and how it affects now instead of just flat surfaces, looking at plane surfaces and looking at surfaces that might have an angle. So that'll be the next step. So the first thing I want to look at is to look at a simple example and take a container with water, for example. So a container with water. Okay, once again, I have that symbol for the fact that we have water at that surface, and that's the surface of water. And the container has a flat bottom. Okay, so it's a flat bottom container, and that bottom is going to have an area called A bottom or A sub B. Okay, so A sub B for A bottom. And the container is also going to have a given height. And it's a very simple container, square container or round container, whatever you want to think of it, but just the simplest form of container possible. Okay, now can anybody figure out what the forces would be on the bottom of the container? So what would the force to the bottom of the container be equal to? So try to think for a minute and try to figure out what the force at the bottom is in terms of area, in terms of height, how you can figure out what the hydrostatic force is. Again, the fluid is not moving, it's it's static, so therefore the only force acting on the bottom is mass times gravity. And to go a little bit further than that, just saying mass times gravity, so mass of the water times the gravity, we can actually go a little bit further and say, all right, we can substitute the mass with rho v, or density times volume times gravity. And now we can put it in terms of A of the bottom times H. So we can substitute for volume, we can substitute that this is equal to rho times G times volume, which would be, volume would be A of the bottom times the height of the fluid. Okay, it's just a dimension of area multiplied by the height. Okay, now hydrostatic problems usually reduce to simple formulas involving centroids and moments of inertia once we start having angles in our system. So if we have a plane surface that is not flat, if we do not have a flat bottom, we can say that the hydrostatic problem is now going to involve simple formulas. So I'll put involves. It involves simple formulas with centroid and moments of inertia. And this is the example illustrated below. So we have this hydrostatic pressure applied to an arbitrary plane surface. So as opposed to a flat plane surface, which we had before, now it's going to be an arbitrary plane surface inside the water. Okay, so think of it like the water is, so this is our free surface of the water, this is our surface height, and water is going to be everywhere around here and sort of pushing down on this plate. And you can see the plan view of that arbitrary plane is shown here below. Okay, so this is the plan view. What the plan view means is that If you were to look at it from the top, that's what the plane would look like. So you can see the plane has a completely arbitrary surface. It doesn't have a shape. Now, the shape of that plane could have been something much simpler, like something like this, okay? And water would just be on top of it and acting with a force on it. But in order to make the problem as complex as possible, we start with the most complicated version, and then we go to a more simplified version moving forward. So that's the idea. So how do we come up with a force for the amount of force that we have on the plate? So we have two forces essentially happening on the plate, right? If the center of gravity of the plate of the sorry, so if the center of gravity of our plate is right here, so we see that our center of gravity is right here, it's reflected as if the center of gravity on the actual plate is right here from a side view. Okay, so from the side, this is the center of gravity of the plate. And we're going to need to know the height of that center of gravity because that's going to be very important in figuring out the force acting upon that plate. And the force acting on that plate is going to be, it's going to be important to find the height of that center of gravity because we know that force underwater and in um, in a submerged surface is going to occur, it's going to change as the depth changes. So we really need to know the depth. We also have a center of pressure drawn here. So this is the center of pressure. This is where the pressure, if we were to reduce it to 1 point, would be centered at. So that's the resultant force actually happens at that point, but the center of gravity is still higher. Okay, so if we were to come up with an equation for force, we would have two different terms now. The first term would say that the atmospheric pressure, which is above our system and is above the free surface, is going to act a little bit on our system, right? We're going to have some effect from atmospheric pressure on our actual plate. So we're looking at the force on the plate. So the first term is going to be pressure atmosphere times the area of the plate. Okay, and then the second term is going to involve the specific gravity of water. So we're going to be, the specific weight of water, or the specific weight of that arbitrary liquid that we have in here. I mean, I called it water, but it could be anything. So we have some liquid here, could be water, could be something else, but we're going to assume it's water for now, but we'll keep it most generalized. So we have gamma times the height CG multiplied by A. So it's as if the force was occurring at the center of gravity, and this force was occurring right here at the center of gravity, and is occurring as if it was a point load. So if we summarize this equation and we sort of bring our terms together, we can say that pressure atmosphere plus gamma times height of CG multiplied by A. And so what we can say is we can define a term called the pressure at center of gravity is equal to P atmospheric plus gamma HCG. That's our absolute pressure. So we're going to call this new pressure, this new term right here, we're going to call P center of gravity times A. Okay, so moving forward from that, we can say that if the plane is submerged, we can write the following statement, and I'm going to write it down fully because I think it's important. So the force on one side of any plane of any plane submerged, so any plane that is submerged, the force so any plane submerged surface, so we have a submerged surface with this plane in a uniform fluid, so it has to be a uniform fluid. Okay, and remember the uniform fluid is the definition in module 1, equals the pressure at the plane centroid multiplied by its area. And this is independent of shape. So essentially what we're saying is that the force on a plane is just equal to the pressure at the centroid multiplied by its area. So it's just the pressure at the centroid multiplied by its area. And we can see that this resultant force is shown right here. So it's the pressure times Cg multiplied by A. Okay, and that's the centroid in terms of the shape of the system. Okay, it's where the center of the shape is. Now, if we create a new coordinate system from our center of pressure, so let's say we have our center of pressure and we say we now have a coordinate system that looks like this on our center of gravity, with our center of gravity being 0. Okay, so this is our new coordinate system. We can figure out from our center of gravity how far our center of pressure is. So the coordinates of our center of pressure okay would be, and I'll put CP in capital. Okay, we have the coordinates are x CP and y CP, okay, on that plane. Now y CP, and I'm not going to derive it because it is a somewhat complex derivation, but y CP is equal to minus gamma times sine of theta. So it depends on the angle. So theta is up here. Okay, it's the angle of the plane compared to the actual system. Okay, so it's gamma sine theta times Ixx, and we'll go over what Ixx is, over PCG times A. And XCP, so the position of XCP, is equal to minus gamma times sine of theta times Ixy over PCG times A. Now, what Ixx and Ixy are the following. So Ixx is the area moment of inertia about the centroidal x-axis. So this is kind of complicated terms, but we're going to try and keep it simple because we don't want to go too far into detail into these problems. This is more for our knowledge and to know how to solve the problems, but we don't want to know all about the derivation. We don't really need it for other things in this class, but this is just to get an understanding of how pressure works when we have a plane that is not simplistic, let's say. So Ixx is the area moment of inertia about the centroidal x-axis, and IXY is the product of inertia of the plate. Okay, now it doesn't really make all the sense right now, but it will make sense in a second once we start seeing what it could look like in terms of more simplistic shapes as opposed to this random shape that we have right now, which would be very complicated to solve for. So the one thing that is really nice about these types of problems is that we can actually use, if we want to, we can use gauge pressure as opposed to absolute pressure. And it makes it a little bit easier because we can get rid of some terms in the equation by using gauge pressure. So in most cases, the ambient pressure is neglected because it usually acts on both sides of the plate. So for example, if the plate was, let's say, a ship vessel or something like that, then one side of the ship vessel would have ambient pressure on it and the other side would have water. So the atmospheric pressure would actually cancel out. So sometimes we like to use gauge pressure for these types of problems because it simplifies our equations. So you can use both types. So the above equations are using absolute pressure, and the equations below are going to be using gauge pressure. And the reason is if we have this system here, and we have pressure atmospheric on this side, and pressure atmospheric coming from the top, then they pretty much cancel out and we can kind of neglect them. Okay, that's the case if we have, let's say, one side of the plate that is not completely underwater. If both sides of the plate are underwater, you should consider ambient pressure, but it usually won't have a big effect. It really depends. But I'm going to write down the equations for gauge pressure as well, because sometimes we might be invited to use them. Okay, so the gauge pressure equations would be force So the gauge pressure equations will be force is equal to gamma times hCg, so the height of Cg times A, so without the atmospheric term, and yCp would be equal to 1 minus Ixx times sine theta over hCg multiplied by A. And here we essentially get rid of the gamma term in this equation. So it makes it a little bit easier to solve because we don't really need to use gamma. Okay, it's two different ways of solving it, but let's put the equations down just in case we need to use them with gauge pressure. And then minus Ixy times sine theta divided by hCg, Cg not Cp, times A. Okay, and the next thing I want to show you is, now I want to show you how you would calculate these values using some simple shapes. So we have in our figures, we have some simple shapes that are described for us so that we can use for solving some simple problems with some simple shapes, essentially. So let me just copy down this one here. So you can see in this, we have, in this figure here, we have different shapes, and with the different shapes, you're able to find Ixx and Ixy. Okay, so you can see that in the symmetrical shapes, Ixy is usually equal to 0. If the shape is not symmetrical, then Ixy is a different shape. And you can just use the values given to figure out what's happening and how to calculate the values. Now, in our questions in the book, they're going to be telling us if we have to omit pressure atmospheric for these problems or not. In some problems, we'll omit atmospheric pressure because of the fact that the plate is touching two atmospheric pressures and we can just omit it. In others, they will tell you to use atmospheric pressure, or they'll just tell you use absolute pressure, or they won't say anything. And then it's up to you to decide, can I make the assumption to omit atmospheric pressure? If the plate is in contact with the atmosphere that you're trying to find the force on, then you're going to be pretty sure that you're going to you can omit atmospheric pressure. If it's completely submerged in water and there's nowhere, or in oil or any other liquid, then it will be harder to omit atmospheric pressure. Okay, so it really depends per problem, but we're going to do an example problem now. So let me copy over the example problem that we're going to do. This is an example problem from your book. So let me copy it over. Okay, so we have this problem. Let me make it a little bit smaller so that we have some space to write. So we have a problem saying a tank of oil has a right triangular panel near the bottom, as in figure E2.7. Omitting PA, so omitting pressure atmospheric, find A, the hydrostatic force, and B, the center of pressure on the panel. Okay, so if you want to, you can pause the video here and try to solve your problem by yourselves if you want to. Now, you can see the book has been very nice to show you what the panel looks like. So the panel is a triangular panel, okay? This is a top view of the panel. Okay, so it is at a certain angle, but it also is triangular. So it's not like a square panel, okay? So just make sure that you understand that. This is as if you were viewing from the top from here. Okay, and we can see that the pressure atmospheric is occurring on both sides, so they tell you to omit it. That makes sense. So let's see at how we can solve this problem. So the first thing we're going to do is we're going to say, all right, we're told we have to find the hydrostatic force. And we know the hydrostatic force is equal to, so the hydrostatic force from our equation is, and we're going to be using the hydrostatic force that we derived for the gauge pressure, because we can use gauge pressure here. We can omit pressure atmospheric, is going to be equal to gamma times HCG times A. And we can convert that actually to rho times G times HCG, whichever we want to use, we can use, multiplied by A. Okay, so the different things that we have to figure out is, the first thing we have to figure out is the height of the CG. Okay, so we need to find the depth of the centroid. Okay, so HCG is the depth of the centroid. So in order to find the depth of the centroid, we just have to look at how deep the CG is. So from our diagram in orange here, we're going to start from a height of 0 here. So we're going to say this is Z equals to 0. And we're going to be looking at the height, the depth up to here. So it's 5 meters plus 4 meters. So HCG, and we do keep it positive in this case. So HCG is equal to 4 plus 5. So the depth is actually positive in this case. And we get 9 meters. Okay. Now, the other things is we're told the density of the oil is 800 kilograms per meters cubed. So that's why I decided to change it to rho G, because we're given the oil density. So now that we have this, we need to multiply by the area. So we need to find what the area is. So the area is just the area of a triangle. Very simple. We know it's a 6 by 12 triangle, so we know that it's 1/2 times 6 times 12. Very simple. It's a right-angled triangle, so it's just half times 6 times 12, which is equal to 36 meters squared. So we can find our force from here. Our force is just equal to 800 times 9.81 times 9 times 36, and we get that this is equal to 2.54 times 10 to the 6th newtons. Okay, and that means that it's equivalent to 2.54 meganewtons. So that's a very big number, okay? So you can see how just from a depth in oil, which has a little bit less density than water, how much pressure and how much force there actually is on a plate at that level. Now, the other thing that we're told is to find the CP on the panel. So to find the CP on the panel, we know that the center is CG. We know that the center of our axis is CG. And we know in order to find Y and X, we need to come up with dimensions that would make sense for Y and X. So how are we going to do this? So I'll give you a second just to think about it. But essentially, what we do is we create X and Y in the direction of the triangle. And what we're going to do is we're just going to plug in values into IXX and IXY. Okay, so we're going to just plug in values into IXX and IXY from the above equations. So from the equation above here, for a triangle, we're just going to use these equations and figure out what IXX and IXY are. Okay, you can see the triangle is a little bit different here, but it's pretty much the same thing. You can just use the same type of idea. And so IXX is equal to base times length cubed divided by 36. So it's the base of the triangle times the length of the triangle divided by 36. So we're going to take the base of the triangle to be this here. So this is going to be B, and this is going to be the length. Okay, and the base times the length is going to be 6. Sorry, let me change colors. 6 times 12 cubed divided by 36. And so that would be equal to 288 meters to the 4th power. Okay, so this is a moment of inertia, so it's a meters to the 4th power. Now, for IXY, our calculation is a little bit more complicated because we have the equation that says is B times B minus 2S times L squared over 72. So the base is, like we said, 6 meters multiplied by 6 meters minus 2 times S. Minus 2 times S. So let's go look at S. What would S be? So in the case above, S is just the width from the top of the triangle to its side. So in our case, S is actually the same as B. Okay, S is just this length from here to the side of the triangle. So S is equal to B. So it's going to be 2 times 6 times 12 squared, the length squared, divided by 72. And that is equal to minus 72 meters to the 4th. Now that's great, but now we need to find YCP and XCP from that. Okay, the eyes don't give you the CP on the panel. The CP on the panel is by finding YCP and XCP. So I'll let you do those in your own time, but you can use the equation that we derived right above for gauge pressure, and you should get a value of minus 0.444 meters and a value for XCP of plus 0.111 meters. So the values can be positive or negative because we agree that it can move anywhere from the center of gravity. Okay, so it can be negative or positive. That's completely fine. And we can say finally that the resultant force, the 2.54 meganewton force, acts through this point. So the force resultant acts through this point. So even though the force is measured at the center of gravity, it actually occurs through this point. Okay, that's very important. Acts through this point. Just like in our first illustration in the diagram, the force actually occurs at a different place where the center of pressure is, right here, where the center of pressure is, and not where the center of gravity is. Okay, so a little bit of a complicated thing, but hopefully it does make sense. Now, what about if, so let me write a question. What about if we have forces on curved surfaces? So what about if we have a pressure on a curved surface? So for example, instead of, now let's take another example where we have a column of fluid, let's say, and on one side of that column, we end our column like this. So instead of having a flat bottom, we now have a bottom that has a certain angle. So in this class, we're not going to be focusing on curved surfaces because it does make it much more complicated. But essentially in this column, you could have air at the top, okay, and then you could have, let's say, some sort of fluid with a weight right here with a weight that is acting on the system, and then you have a second fluid here with a weight that's centered a little to the left with another weight. Okay, so we have like three different parts to it, and then our air also acts upon the surface here with a weight of air, for example. And in this case, what we can say is we have different forces, right? So we have forces that are occurring on this side. So we have a force 1, let's say, that's acting like this. And we have another force horizontal this way and a force horizontal this way. Okay, some horizontal forces. So let's just call them horizontal forces instead. So we have horizontal forces on each of the parts of the fluid. And then we finally have a vertical force here. And the vertical force is going to be a little bit offset. It's not going to be directly centered. So we can figure out from the same kind of technique where the forces would be located within the system. And if we do the sum of the forces vertical, the sum of the forces vertical would be equal to, so this is W1, okay, and then W2 and W air. So we would have W1 plus W2 plus W air would be equal to that force V. Okay, so this would be the sum of the forces in vertical. So let me just write sum of forces vertical would be FV on one side is equal to everything counteracting FV. Okay, but we're not going to go into it for this class since it does become quite complicated and there are other subjects that are more interesting that are outside of hydrostatics that we want to get to as well. And mathematically, these get somewhat complicated. And since this is not a hydrostatics course, but more of a transport phenomena course, we're going to focus on the transport phenomena side a little bit more. So the next thing I want to talk about is buoyancy and stability. So this is the next big part in this chapter, which is called buoyancy and stability. And buoyancy is obviously very important for a lot of things in engineering, especially floating boats and any floating body. Okay, this is really important, but it's also important for bodies that are submerged, such as submarines or stuff like that. Okay, we need to use buoyancy in any case and for diving and for many other things. So the first thing we can say is that the same principles that are used on the surface can be used on submerged surfaces. So the same principles used on a surface can be used on submerged surfaces. And or on any floating bodies. Okay, so we're going to apply what we've learned so far and apply it to submerged surfaces and floating bodies. And for this, we're going to have two different laws that were created, and those are the laws of buoyancy. So the laws of buoyancy state that one, a body of fluid experiences a vertical buoyant force equal to the weight of the fluid it displaces. Okay, so this is a little bit of an explanation of what's happening, but a body of fluid experiences a vertical, and I'm going to write it all out because I think it's important to have it written down, and you can think about it while you're writing it down as well. So experiences a vertical buoyant force equal to the weight of the fluid it displaces. So it essentially means that if we have a body, and it doesn't necessarily have to be a body of fluid, but it can be a body of any type, it experiences a force that is equal to the weight of the fluid it displaces. And we're going to look at what that actually means in terms of an image. Okay, the second one states that a floating body displaces its own weight in the fluid in which it floats. So a floating body displaces its own weight in the fluid in which it floats. So that means that if a boat is on the water, the boat is going to be a little bit underwater and is going to displace the amount of water that is equivalent to the weight of the boat. And the water is more dense than the boat, therefore the boat is not going to sink. Okay? And if that doesn't make complete sense right now, hopefully it'll make sense in a little bit. So let's look at this from a methodology of integration. So let me copy this over so that we have it as reference in our lecture. Okay, so we have this integral method to figure out how to understand buoyancy. And the integral method might not be the most simple way of seeing what's happening, but it does help out in the sense that it does give us a mathematical understanding of what's happening. So once again, we're going to take that a positive is going upwards. And what we're going to define here is we're going to say that in part A, we're going to say that, so if we look at part A, which is on the left side, okay, it says two different approaches to the buoyant force on an arbitrary immersed body. So on the left side, we see that we have a surface 1 and a surface 2, okay, a surface somewhere inside water at the top and then a surface at a lower curved surface. And we see that there's a force vertical at the top going down and a force vertical at the bottom going up. And what we can say is that the buoyancy force, so the force of buoyancy, is equal to the difference between those two. So it's equal to FV2 minus FV1. Okay, so we took a positive going up, so it makes sense that FB is equal to FV2 minus FV1. Okay, that's just the buoyancy force. It's the amount of force that is giving the system the right to float or not, essentially. So if force vertical 2 is higher than force vertical 1, we will have a system that moves up. If force vertical 2 is equal to force vertical 1, the system will be in equilibrium. If force vertical 1 is greater than force vertical 2, then we have the system will be sinking. Now, the integral method of looking at this is to take a horizontal element with an area DAB and to say DAH, sorry, DA height, okay, is to take that and say, all right, this would be part B, okay? So the integral method is to say FE is equal to the integral of P2 minus P1. Okay, so instead of the forces, now we're looking at the pressures on an element times DAH. And remember, we know our definition of pressure is minus gamma times Z2 minus Z1. So we can substitute this with minus gamma outside of the integral because it's a constant, multiplied by Z2 minus Z1, and it's a constant for liquids in this case, times DAH. Now, do you see what Z2 minus Z1 times DAH is? So this term right here, and the integral of this term is actually equal to the specific weight multiplied by our body volume. So it's a specific weight multiplied by the body volume. Okay, pretty interesting. Okay, so if we want to talk about this in back to part A, if we want to look at part A and we want to look at it as more of if we want to look at it more in terms of text, we would say that the weight of the fluid displaced is equal to the fluid weight above surface 2 minus the fluid weight above surface 1, just to look at it in terms of weights. Okay, so In this case, we assume that the fluid has uniform specific weight. So we assume that there's a uniform specific weight. And we know that the line of action of the buoyant force passes through the center of the volume. And we can say that the center of mass, because the center of volume is actually also the center of mass because we said it had uniform density. So we're going to say we assume fluid has uniform specific weight. And what we mean by that is that it has uniform density. So density is uniform. And if density is uniform, that means that the center of volume, so the center of the shape, is equal to the center of mass of the shape as well. Okay, because the shape has a uniform density. Okay, now the force of buoyancy acts on this center of volume, or center of mass. The force buoyancy acts on this point. And we can label it, we can call this the center of buoyancy. Or we can label it CB or B sometimes. Okay, now if we have a different example with the fluid being layered, so let's say we now have, instead of just a regular fluid, we now have a layered fluid. So if the fluid is layered so that it has different densities and they are not uniform, then you have to take into account the buoyancy. So for example, an idea would be you have a boat that is in water for half of it, and then there's like, so this would be water, or this would be oil, for example, and then this part would be water. You would have to look at the buoyancy of the boat. So you'd have to look at the buoyancy of the boat in terms of the oil and in terms of the water. So the force of buoyancy for a layered fluid is equal to the sum of rhos times g times displaced volume. So what you do is you just treat them as different system and you look at the displaced volume for each system. And you look at the density of each system separately. So floating bodies are a special case. So this is for completely submerged bodies, but floating bodies are a special case. Why are they a special case? The reason they're a special case is because only a portion is submerged. So an example of a floating body would be something like this. So you would have a ball type system, and you would have to separate the system into two pieces. So you have, for example, water here, and above you have air. So you would have to figure out, you would have to essentially figure out the system in two pieces. So this piece right here, underwater, would need to have a center of gravity that is just for that part of the system, and our force buoyancy would be acting upon that center of gravity. So we'd have a point B that is inside of that half that is underwater. Okay, so we'll look into that a little bit more in terms of, so essentially, if we were to redraw this in white on the side, we have a center of gravity, CG, with some weight, and we also have a buoyancy force counteracting that center of gravity. And our force of buoyancy in this case would be equal to gamma times displaced volume. And the great thing with buoyancy is that it starts making a lot more sense once you start doing some problems. So gamma times the displaced volume, which is the displaced volume of the water, so we displaced this much water essentially, okay, we displaced the amount of water, is equal to the floating body weight. So the amount of water displaced is actually equal to the weight of the floating body. So if for example, if a boat has 100 tons, is 100 tons heavy, it will displace 100 tons of water. But part of it might be above the surface. Now, we also should take into account the displaced air that the system has displaced. But we neglect this because the density of air is so low. So we neglect the displaced air. Okay. So moving forward from this, let's try and do an example just to get us to understand what we've just derived and if it makes sense to everyone. So I'm going to write down the example. A can in the following figure, so I'll draw the following figure. A can in the following figure floats in water and we're told to find what is its weight in newtons. So we have a can in the following figure, which I'm going to show you in a second, floats in water. What is its weight in newtons? So we have this figure. So the figure looks something like this. So we have the can, and the can is in a receptacle of water, and here we have our symbol for the surface, okay? And under the surface we have water, and above the surface we have air. Okay, this is our can. And we're also told that the can, and this is actually a real can, so it's the real size of an actual Coke can. So the can is 9 centimeters wide, and we're also told that the surface, 3 centimeters of the can is above the surface, and 8 centimeters under the can is below the surface. Okay, how do we figure out what the weight of the can would be? So we can use our floating formula. So our floating formula is here above. So we have floating bodies are a special case, only a portion is submerged. And we're told that FB, force of buoyancy, is equal to gamma times displaced volume and is equal to floating body weight. So what we're trying to find is the floating body weight. Okay, so we're going to write this equation down. We're going to say FB is equal to the weight, floating body weight. Okay, so this is floating body weight. And it's equal to gamma times displaced volume. Okay, so we have gamma times displaced volume, and we can find gamma either from table 2.1, or we can use rho g from table A3 in our appendix. So we already know very well what our 2.1 value is. It's 9,790. So let's use the other one just to practice. So in appendix A3, we're given that rho is equal to 998. And I'll just go to the appendix really quick just to show you. So in table A3, we have for water 998 density. Okay, so the density is equal to 998. Then, so we can say that gamma is equal to rho g, and so we're going to substitute rho g in it. Now, the force of buoyancy doesn't really matter. We don't really need to look for the force of buoyancy. We know that the force of buoyancy, because the can is floating, is equal to the weight displaced, and the can is not moving. So what we're going to do is we're going to use this side of the equation. We're going to find the weight of the can from the amount of water it displaced. And the amount of water it displaced is just the volume times the density times the gravity. Okay, that's the actual weight of the water that it displaced. So if the can wasn't in the water, you would have water all over the surface here, and the water would just be within this system here. So what we're doing essentially is we're trying to figure out, and I'll draw it in blue, we're trying to figure out what weight in blue here did the can displace from the water. And that's the weight of the can, because that's the amount of weight that the can took away. Okay, so we have that the weight is equal to 998 multiplied by 9.81. Okay, that's our rho g, or our gamma for water in this case. Okay, W. And multiplied by the displaced volume that the can has displaced. So what's the displaced volume of the can? Well, we can write it as height h multiplied by the area, the cross-sectional area. So the height of the can is going to be 8 centimeters, so that's pretty easy, 0.08. So 998 times 9.81 multiplied by 0.08, and then multiplied by the area. So we know a can is a cylindrical system, and we're going to assume that the can is a perfect cylinder for this. So we're going to use pi times diameter over 2 squared. Okay, so we're going to use pi r squared. What's the radius? Radius is 9 centimeters, so 0.09 divided by 2 squared to find the area. So that would be the area. And we find out that our value is 5 newtons. So the weight of the can is 5 newtons. And turns out that this value here, okay, so this value here is the displaced volume of water. So you can see how simple it would be to measure the weight of something by just submerging it in water and figuring out how much weight, how much displaced volume there is. And with the density of water, we would be able to figure that out. Now, to finish off this lecture, and in our in-person lecture on Tuesday, we will be doing some other example problems of some extra things with buoyancy and rigid body motion. But I want to finish off this lecture with pressure distribution and what would happen to pressure distribution in rigid body motion. So just to get an introduction to next time. And that'll conclude this part. So the next thing I want to talk about is called pressure distribution in rigid body motion. And the question is, what happens if we move or accelerate a body with a liquid in it? So now we're not just going to keep our system from staying static, we're actually going to start moving. So what happens if we move our system? And if we accelerate a body with a liquid in it? So think of a cup of water, and you can actually do this at home. Try it. Just fill a cup of water halfway and move it from left to right very, very fast. What happens? The particles will start moving from left to right, but within the cup, right? So the particles are not actually moving within themselves, but we do create a pressure on one side. So by moving the cup from left to right, we actually create a pressure on one side. Okay? So what I want you to think about, so I'll just write down what it actually does, is all particles are in combined translation. So when you move your cup from left to right very, very fast, all particles are in combined translation. And so all the water particles are kind of moving together, right? They're moving together. There's no relative motion between the particles. So if we move a cup from left to right and we don't stir the water or anything like that, let's say it's a perfect movement from left to right, we're not going to get any mixing of the particles. So we can say that therefore there will be no strains in the system. There's going to be no strains and no viscous forces. Okay, again, this is an ideal system, an ideal world. Okay, so there's no viscous forces. However, there are pressure forces. Okay, now there's a pressure force from us moving the fluid from left to right very, very fast inside the cup. We're creating this pressure on one side of the system that is moving the system from left to right. And what I want you to observe is what happens to the fluid when you do that. Okay, and I want you to observe that before next lecture because we're going to talk about it in an example. But before we look at that, let's recall our equation that said that the sum of the forces is equal to F press or F pressure plus F gravity plus F viscous. Well, we just said in a rigid body motion system where we have a rigid body covering water with a liquid in it, we wouldn't have any viscous forces because our viscous forces are pretty much accounted for because nothing really moves. And we had said that this sum of forces is equal to rho times A, right? This is the total acceleration. So now our system, instead of just having gravity, now also has a new element to it. And that new element is the force of pressure. So we have our gradient of pressure. Okay, our force pressure is the gradient of pressure plus rho g is equal to rho times A. That's the total acceleration multiplied by the density. And so we can see that the pressure gradient is going to act along a line, if we rearrange the equation and bring rho to the right side, is going to act along with gravity and acceleration. So the pressure gradient, so the change in pressure, acts in the direction of G minus A. And I want you to think about what that means, and we can discuss it in our live lecture next Tuesday. So this concludes our video lecture series for Module 2. We will be doing some example problems at the start of our in our live lecture, which is next Tuesday, and we will discuss what will be on the quiz as well on that day as well. So I'll see you next Tuesday. Thank you for listening.